Employee, your microphone is on. Employee, your camera is on.
Sir, good evening.
Good evening, sir.
Hello.
How are you, sir?
Please start your class, sir.
Okay, sir. That's fine, sir. So the thing is that today our topic is fundamentals of radiations. As you know that yesterday we are discussing about this that is radiations and particular nuclear radiations. So in this nuclear radiations, how the things is associated, what are the fundamental particles are present in this nuclear radiations? What are the things happened? How the that nuclear radiation happened? What are the particles are responsible? Then how the that is what is the nuclear decay is there? How what's the law are associated? What is the that is effect on our body and all the things? So we have to go through that one. Okay. So in the next, that is the atom. You will say that is the structure. If we calculate the structure of atom, so there is major three fundamental particles found in case of atom, right? So I yesterday I just told you some that is this that fact. So some fundamental particles are present. So I told you that 17 particles are present, but basically the three major fundamental particles are associated with this atom. So first one is, you know that atom has two that part. One is nuclear part, and second is that is outside of the nuclear part. Inside the that is atom, the two parts are there. One is nucleus, second is outside of the nucleus. Okay. So if we discuss that is inside the nucleus, that is what things are present. So inside the nucleus, that is proton is present, and neutron is present, and electrons is also present. So the in proton is that, what is the nature of the proton? Proton is that is positive charge particles. It is present inside the nucleus. Okay. So inside the nucleus, two things are present. That is your two major fundamental particles are present. One is proton, second is neutron. So that is, what is the nature of proton? Proton is the positive charge particles. Okay. So that is the unit is 1 AMU, that atomic mass unit, and it determines the elements. So that is, it is the actually the proton is the fingerprint of that particular elements. That is you know that the atomic number is that can specified is associated for a particular atom. So like that hydrogen atomic number is 1, helium 2, lithium 3, beryllium 4, like this. So that is, it is that it is the number of protons. So number of protons which is present inside that particular atom. So on the basis of that atom, that atomic number is identified. Okay. So if you come down to another that is fundamental particles, that is your neutron. So neutron is neutral nature. It doesn't contain any kind of charge. Means it is not neither be that is deflected or attracted by the magnetic field. So it is considering that is to giving the mass. But in the case of that is neutron, that is one important thing is that in case of inside the nucleus, that both proton and neutrons are present. But in a particular atom, so maybe the number of that protons always same. In a particular atom, number of protons are always same, but maybe the neutrons are different. If we take the example of hydrogen, hydrogen has three isotopes. One is protium, second is deuterium, third is tritium. Okay. So that in case of protium, that proton is 1, atomic number of hydrogen is 1, right? So but hydrogen contains three isotopes. So proton is 1, that neutron is 1 also in case of protium. If you come down to the deuterium, so that is proton is 1, but neutron are 2. Okay, neutrons here present are 2, number 2. So in case of tritium, so that is proton is 1, neutron is 3. So on the basis of that mass, that is varies in case of protium, deuterium, and tritium. As number of protons are similar in the case of that is hydrogen. So all the three that isotopes has the similar number of proton. That is number only one proton is present in case of protium, deuterium, and tritium. So these things that indicate that their chemical properties are similar. So the chemical properties of protium, deuterium, and tritium are almost equal. Okay. So but the thing is that only the physical properties might be the different. Okay, definitely it is different. Okay. If you come down to the third charged particle, that is your electron. So electron is the negatively, it is the negatively charged particles, and it is it's present in the orbit of that nucleus, means outside of the nucleus and moving around that orbit of that particular nucleus. So determines atoms reactivity. How does the atoms react in this case? So because the that flow of electron, always transformation of electron from that lower energy level to higher energy or higher to lower, that depends depending upon the situation. On the basis of that, that is if that an atom, if we say, if an atom readily lose its electrons, it is electropositive in nature, means it is sometimes, you know that all the metals try to lose their electron faster way, so that is metallic nature indicates to the, that is particular loss of electron. Okay, that you can say the oxidation. So but in some, so in so many atoms that accept electron to become the stable configuration. So in this case, if we take the chlorine, so chlorine is but that is in gaseous state, it is non-metallic in nature and gaseous state. So that's why it accept, maybe that depending upon the situation, the atom may donate the electrons or may accept the electrons. So that is the electron is that is if we accept the electrons, so non-metallic in nature, and that is if we donate the electron. I just give an example of that one. So that is well confined examples is if we give the donate the electrons. So that means higher energy level to lower energy level, lower higher orbit to lower orbit, or lower orbit to higher orbit, they are changing their position. On the basis of that, they are actually chemical behavior depends upon the situation. Okay, if we go down the next slide, we will see. So that the thing is that nuclear arithmetic. So this is an important part of that. Is, you know that these things we have discussed already. So proton and a neutron are collectively called nucleons. So inside that that is if nucleus is otherwise known as nucleons, because collectively that proton and the neutrons both are present in the nucleus. So this combination fact is called a nucleons. So individually you can say proton and a neutron, but a combination you could say the nucleons. So here that is a, if you say the a is the nuclear number, or you can say that atomic mass. Okay, z is equal to atomic number, and x is the chemical symbol. Okay, whatever the atomic, that in the upper part of that, any if you write down that anything else, so that is in the middle part, that if you write down the chemical that is symbol, so maybe hydrogen, hydrogen, helium, lithium, whatever maybe. If you try to write down the helium, so in the upper part there will be the atomic that is atomic mass. In the upper part atomic mass, and lower part is the atomic number. If we consider the helium, so helium will be the symbol He, and in the upper part you have to write down 2. In the lower part you have to write down, upper part you have to write down 4, that is atomic mass, and the lower part you have to write down 2. Okay, atomic number. So that is the representation of it, means arithmetic of this particular nuclear arithmetic. Okay, if we come down, that is number of neutron is a minus z, that is formula is a minus z, and the nucleons number of an isotope is written in the suffix of example of that is I told you yesterday. Okay. Next, come down to the radioisotopes. So this is an important fact when you are discussing the radioactivities of the particular elements. So the radioisotopes is important area of that one. This is connected to the radioactive behavior. So let's understand this one. Not all atomic nuclei are radioactive. So that is here we have conclude with one statement that not all atomic nuclei are radioactive in nature. If we say all the that atoms or that is are radioactive in nature, it is wrong in case. Okay, so why it is wrong? Because see that we'll go to that explanation. If we'll see, if anything will absorb the that is energy, and it is it emitted something something factors like x-ray, y gamma, gamma, x-ray, gamma, beta, and all the particles like that, that scattered particles. So that is really radioactive in nature. So but all the actually elements, all the elements would are present in that is they are not radioactive in nature. Some nuclei are stable, while others are radioactive. Okay, some nuclides are stable. Almost all, that is, we yesterday we have discussed about that. And five, almost all out of five, that is members are radioactive in nature, and 50 are stable on the basis of that calculation. Okay, so those that are radioactive are sometimes referred to as radioisotopes. Okay, those who are radioactive, they are sometimes referred to as the radioisotopes. If you consider, okay, if you consider, that is, think as a carbon. Carbon has three isotopes. So carbon has three isotopes. One, this is C12. 12 is the upper part. 12 is written. That is your atomic mass, and below there is written, that is your atomic number. Means number of proton. In case of this example which is given, carbon has atomic mass 12, 13, 14. Carbon 12, carbon 13, carbon 14. So in all the cases, atomic proton number are that is 6. So first one is the stable form. Okay. Second one also, C12 is also stable form, because you know that C12 is the general that is carbon which is associated with us in our daily life. So it is in stable form. But that is second also for your kind of C13 also in stable form. But C14 is radioactive in nature. How does it? How can define this one? So I have to explain in later. So now that come to the point, radioactive decay. This is another important area of radioactive decay. So this, because this particular thing, radioactive decay, is associated with some segments that of that is behavior of radioactive radiations. So that is the most important point of the radioactive decay. Okay, so this thing is radioactive nature. You know that radiation has highly that is hazardous things. You know that that sometimes we are discussing about that right now, that World War II, 3. Okay, so if you come down that part, or Hiroshima, Nagasaki, you have seen that things when that that is USA that is bombarded in the Japan, in Hiroshima and Nagasaki. What happened? Till date, the same radiation is active there, and peoples are suffering. So nowadays, that time it's 1947, 48, 46, whatever, I don't know, that is when that is World War happened. But thing is that by that time, that what is the development technology was there. Right now, that technology is somewhat different, right? So that that much more radiation will be there in this case of if any kind of a nuclear bombardment will be done. So come to the point of that, and that is why the radioactive decay is that a most important area of this radioactive that is the behavior of that is radioactive nature. So radiation from radioactive materials is the result of the radioactive decay. See what I told you. Actually, when any kind of a radioactive, see, if we take the example of a carbon 14, okay, I'm taking of the carbon 14, so it is radioactive in nature. So if carbon 14 shows any kind of a radiation, that is your radioactive decay. So radioactive decay, I told you very honestly, radioactive decay means the radiation associated with that particular that is radioactive elements. When anything will be fall down, okay, if you come across, if you see, okay, let me to give another example. So if you see, if you come across with the medical hospital, and you have gone to the any kind of that is X-ray or the MRI of that is segment of that particular pathological service, you'll see that in front of that particular that is, door, or that is in the area of that radioactive radiations is mentioned about in the yellow color, and one triangular shape of that things is there. So that means, and one more thing is that, so that is okay, that is the radiation area. Okay, but there is, okay, in medical hospital segment, so radiation level is low, it's control level, that machine whatever they are using, so that is control level. But think is that there is radiation. Okay, if one person will continuously work in that radiation, there will be the effect. Yes, obviously there must be the effect on that fellows. So that's why if you see that sometimes I will come to the point. So sometimes that is if you go for the that any person is that is that in the having carrying that a baby, so continuously you don't go for the X-ray, right? So that is not allowed. Okay, 1-2 times, okay, that's fine, but more than that, it will affect that child which is that inside the womb. So that's why radiation, why I'm telling you that is that there that wombs containing that is a small that is a small part of that body which is depending upon the mother's womb. So that cannot be that is tolerate that kind of radiations. So radiation is something different kind of behavior. So that's why you should be careful. So that decay is means the radiation. Decay means the radiation. So radiation is anything that radioactive elements, materials, the results radioactive decay. This radiation which is formed by these particular radioactive elements, that is known as the radioactive. Very honestly, very true things is this. So that is known as radioactive decay. An atom with an unstable nucleus will decay until it becomes stable atom. Okay, now the thing is that why it happens. See, always the basic facts of the chemistry, if you understand basic thing, if I'll say that one line of chemistry, that always anything, atom, compound, molecule, whatever you can say, that they are trying to be stable configuration. I don't know when the teachers tells like this, will the teachers tell like this, that stable format. So we have to explain that stable format means lower down its energy, means energy will be lower down. So once energy, see that it will come down, I'm telling when I'm explaining the facts, it will take two magnets and having the same pole, means north pole to north pole, face to face. Then what will happen, if will come, it will make them close, there will be your hand will be vibrated, your hand will vibrate, actually the magnet will vibrated, which, yeah, if you are carrying with your hand, so it will be vibrated. Okay, because that's why the repulsion mechanism is there, repulsive force. If we bring them in the alternate, means that is north pole to south pole, they'll what is that, they will attract and they will fix with each other. So that is why when the higher level of energy will be there, so which associated with the nucleus, there will be a vibration. So that vibration helps to the that vibration helps to cause to the, that is what is radiation, that vibration. So when what till how much it will be, that the vibration will be it will be that is gone. So that when the energy will lower down and they have a stable configurations. So that is why that is actually that particular area of that energy is radiation. That particular area of the energy is radiation. Suppose if we take the, if we say so many things, so many times if we come across the things nowadays, the global warming, right? If I gave the example of that one, that is how the energy, it is not actually that that is your radiation of that particular radioactive radiation, but it is radiation. Global warming, if we say that if come across the nowadays weather is become hot and hotter and hotter, and I don't know that what kind of weather behavior is there. Sometimes it's very cold, sometimes it's very hot. Now in the that somewhere else the high ice falls is there in the Himalayan, and that is all areas where somewhere in the heavy rains are there, where this is the summer season. Actually the thing is that that we don't know what kind of behavior this is due to. This thing is happening due to the global warming. Okay, because multiple behaviors of that. So thing is that before some years, if we go down to 15 20 years back, 20 years back, so there is lots of plants available. Okay, but now instead of that is plants, that is concrete building. So what happened there? When sunlight will fall on that concrete building, that building will be heated. Okay, that building will be heated naturally. Okay, that sunlight is there and everywhere, that all the atmosphere are hitting, because due to the summer and the sunlight is very strong, that come close towards the equator. So that's why what is that everything is heated. Okay, but the thing is that after that, then when the evening comes up, night comes out, then there are that where there is plants and that environment is that is surrounding areas are there around that building. So now the building when come down, that there is no sun. Okay, so it will be release its heat to the surrounding. That building release its heats to the surrounding. That what you say, you now you understand that building has a capacity of holding up that is what heat. That capacity of heat it can hold, not more than that. If more than that, it will burst. Okay, so the capacity of holding that heat is That is, there is a some amount of capacity of holding. When that will be maximum. After that, when the weather surrounding is cool, then it releases its that heat towards the surrounding, because the surrounding is cool. It is system and the surrounding relationship. If you come, if you think about that, what is your uh, thermodynamics, system and surrounding. So thing is that what will happen here, suppose if we say, it will take hot water in a glass, in a steel glass. Okay, the surface of the steel glass will be hot on an average to that is water. Okay, but as much as time it will keep the open and all of the surrounding is cool. Okay, so the transformation of energy will be done from the that glass towards the that is surrounding. Okay, then the what is that part, that is known as your radiation. How much energy is transferred to make it stable, means make it original condition, so that amount of energy is known as your radiation. It's simple things. Radiation is simple things, but I am telling you about the nuclear radiation. It is not nuclear radiation, it is simple radiations. Okay, simple heat radiations, you can say. You can take, if you are you can give the name of these radiations. Radiations means transformations to come down the original situation. Here the thing is that when this particular that is see that that atom with an unstable nucleus will decay, means radiate, until it becomes stable, emitting radiation as its decay. So this is the point what I mean to say. What do you mean by decay? So atom is unstable. To always atom try to stable, make itself stable. Okay, so the stable due to the high amount of energy, so it emits the energy. It will be emit the energy. Okay, it will not absorb, it will emit the energy to make down its energy level, come down into the stable condition where there is no that is emittance of energy. So that amount of energy is known as radioactive decay. Okay, now the radioactive comes from the atomic nucleus, not from the electron clouds. So next point, a radioactive comes from the atomic nucleus, not from the electron cloud. So electron has no role in this case. Electron has no role. Only the proton and the nucleons, that nucleons show these behaviors. Electrons will come, go, that is not the part. That is depending upon the that is chemical properties. As you know that, one more interesting thing. See. So radioactive elements still date, that is research is going on, but thing is that a very tough condition, because there is hazardous things are there. So that's why the scientists are not getting proper that is how they will do this kind of things. So the chemical properties, nowadays it is going on, but thing is that it is not accurately, it has not done. So the thing is that the scientists are they're unable to find out what the chemical properties of this radioactive elements. If you ask me what is the chemical activities of uranium, I can't say. So because chemical electron are associated with the chemical activities, going, coming, that is an atom release electrons and accept electrons, that is the chemical properties. But I told you, when I started this topic, I told you that proton and a neutron are not taking part in the chemical reactions, so they are taking part in this case of energy levels and all the things. So that's why that how the electrons are revolving around the nucleus. That you know to understand that the things of electrostatic force of attraction, as well as that is magnetic force of attraction which there, nuclear force of attraction, that is shielding effects and all the things. So these are force of that attraction are associated with these particular things. But thing is that here the thing is that radioactive comes from the atomic nucleus, not from the electron cloud. So electrons are not associated with this radioactive behavior, but the radioactive behavior is done by the nucleons, that means proton as well as neutron. Neutron is not taking part of this one, but proton is taking part of this one, as both are staying inside the nucleus. Without instruments, radioactive cannot be seen or felt. But that is actually that cannot be seen. Okay, that's fine. But felt means, okay, that I'm that little bit of contradictory of this thing. Okay, no problem. I will correct that one. But smell, tested and detected by the human beings cannot, but felt. There is no smell of radiations. There is no taste of radiations that cannot be detected by the human beings without but felt, because that thing will give the hazardous impact on our body. So that's why we can feel that. But it is okay. The thing is that next, for this reason, it went undiscovered until this century. Okay. Now, where does radiation come from? How radiation happens? If you see this particular picture on your screen, if you see how radiation takes place. Radiation results from an unstable nucleus. See that H3. This is the tritium. Okay. So inside that electron, one electron is there, one proton is there, and two neutrons are there, right? So if you see that elaborate of things, that d electrons is there in the electron cloud. One electron, you know that hydrogen has one electron and one proton, and a deep blue mark of that one is known as your proton, and the two light blue that is circles are known as your neutrons. So in tritium, I told you that the three things, that is that atomic mass is 3. So atomic mass depending upon proton and neutron. So one proton, two neutrons are there in the H3 molecules. Then what will happen? H3 molecules, now one proton, two neutrons are there, but it will converted to that it will actually that they want to be lose its energy. Okay, so that's why one another two out of two neutrons, one neutron again converted to the proton. So when one neutron neutron converted into the proton inside the nucleus, that is the sense energy will be changed. So that how much energy is that emitted by this process, that is known as your radioactive decay. These simple things. The proton will convert it to the neutron will convert it to the proton. That is what you say inside that is your sun. It is fission and fusion reaction is there. Okay, fission fusion, you have learned this one. This thing is one neutron converted into the proton. So one neutron when converted into the proton, the amount of energy will be emitted. That amount of energy, how much amount of energy is emitted, that is your radioactive nature. So that means, see, that is, it is not one, if one proton is there, no neutrons are there. If you say the hydrogen, that you can say the protium. So it is not that is radioactive in nature. Okay, and the deuterium, it is not also, it is somewhat in that is radioactive. One another neutron is there, so it will convert somewhat in the some mild having that mild having. But in case of tritium, it is strongly radioactive nature because two neutrons are there which can be interchanged to the proton. So the amount of energy decreases in this format when that one neutron is converted to the proton, again one proton. So in the first case, if in the picture, one proton was there, but in the second right hand side picture, you will see two protons are there, deep blue, two protons. So one neutron converted into one proton. So the energy, what is the energy is decreases, emitted in the form of energy, that is known as the radioactive decay, or you can say it is the radiation. It is the radiation. Next. Then if you come down radioactive decay, the radioactive decay is a random event. Random event means it will interchange. I gave you the example, best example of that one, that is your sun. Hydrogen to helium, helium to hydrogen. Hydrogen to helium, helium to hydrogen. So helium has two protons, atom number 2. Hydrogen has one proton. If hydrogen in the hydrogen, tritium is there. Suppose if you go down this particular thing, okay, picture. So in the first, in the left hand of your, that is one, and that is one proton is there, two neutrons are there. But in case of right hand side, how many protons are there? Two protons are there. Two proton means atomic number 2. Atomic number 2 indicated towards which one? That is helium. This is the nuclear fission and fusion. Again, that particular proton, which is that is that neutron which is converted into the proton, in case of right hand side, If that proton again will convert it into the neutron after gaining some energy. I lost my energy. I come down to the position number 2. When I'll gain again the energy, I'll go to the position number 1. That is interchange. It happens. That's why if you have remember this thing that your in case of a nuclear fission, what will happen? 1 break down into 2, 2 break down into 4, 4 break down into 8. So like this. This is the bombarded method. This is corresponding bombarded method. And in the corresponding bombarded method, that thing is that it's going on, and energy will be released. That's why atomic that's what you say, the atomic blast, that nuclear blast. So that's happened. It's a continuous chain of reactions. Reaction will not stop. But okay, if you ask me that how it happens, it is continuously. Again, that is poison is used to stop the reactions in this case. So that's why there's a control command when given over there. Poison is that is given. So due to that, the stop that is your atomic reactions will be stopped. Okay, but these things happen in the sun. And for your kind information, that sunlight you are using, that's why. For your kind information, that's why sunlight has that. What is that? That your radiations, UV. You are getting UV from the sunlight, and that is absorbed by the which one? By the ozone layer. So that cause the radiations. That is the UV ultraviolet ray, which is caused by the sun. It is due to this process: hydrogen to helium, helium to hydrogen. First, hydrogen that was there, 2 neutrons are there. So due to that, that unstable energy was there, and to become the stable, that releases that particular energy. So now it releases the 2 protons. When the 2 protons are there and it got some energy, so again it will have the higher energy, but it will be interconvertible to the hydrogen. So hydrogen to helium, helium to hydrogen. This process, fusion and fission, is going on inside the that is sun. So that's why. So that is that particular things is happen. Okay, that's why that radiation is there, UV ultraviolet ray. Okay, if you come down these things, radioactive decay is random event. It is going on. Random event. Half life is the time it takes for half of the nuclei is a substance to undergo radioactive decay. So what is half-life? Half-life is the time it takes for half of the nuclei is the substance to undergo radioactive decay. So this is the half-life. Half-life is an important area because we cannot calculate the full things. So now you will come down the electromagnetic spectrum. So radiation that can transfer enough energy to remove electrons from their atoms are referred to as ionizing radiations. So one term here is ionizing radiations. So radiations that can transfer enough energy to remove electrons from their atoms and are referred to as ionizing radiations. Okay. So here the thing is that also that that electron is also transferred from the atom to participate in the chemical reactions. So some energy will be exothermic and endothermic, if you understand that thing. So when the electron will go away from the atom, so it will convert into ion. Okay, that is your ionizing radiation. Also, that some amount of energy will be, but it is not that hazardous. This is found in the high frequency that portion of the electromagnetic spectrum. This is only find out in this case. Okay, now come down. Radiation in research. Okay, radiation and radioactive materials can be valuable tools in research. Yes, and that you will see that E is equal to MC² formula that is discovered by the Einstein. Okay, so E is MC². That is that do on the basis of that formula, that is that atom bomb, what is, you could say, nuclear bomb is discovered. But that what is the see that actually that if I'll say lots of that is use of these new radiations in better human betterment. Lots of. You will see that a cancer. So chemotherapy, okay, that is a type of radiations. The cancer carcinogen that viruses can be eliminated by this kind of radiations. Lots of people say that your electricity now, if you go to that any kind of Western country or European country or USA, that is electricity failure of electricity is zero. Every day and night electricity is going on. How? This is the due to the nuclear plant. Also in India, that is nuclear plants are there, so we are providing getting the electric. But okay, so thing is that in the research segment, if you go to the space, they're using the nuclear radiations for their research. It'll surprise you when you'll see that space research and all the things. So 1,000 crores of that is human that perspective point of view, betterment of human perspective point of view. So you can use the this radiations, but there is also bad use of this one, like that I gave you an example of a nuclear bomb. Okay. Now the thing is that radioactive materials are used in a variety of STEM. Anyone can say that what is the STEM? What is the full form? Can you know? Do you know anyone else that what is the full form of STEM? Okay, this is the modern technology, science, technology, engineering, and mathematics. STEM. This is STEM is actually this STEM nowadays you are using. STEM is a very huge organization in USA, research organization. Science, technology, engineering, and mathematics. Okay, so that means this is the STEM. So the STEM disciplines means in case of science, in case of technology, in case of engineering, in case of mathematics, you can use this radioactive that is radiations. So ranging from the biological science to physics and material science. So these are the use of this one. Okay, there are several lab approved to use the radioactive isotope at UAH. So when you can use also, if you say that sometimes it is that biological segment like your treatment of a cancer, as well as nowadays that is uh, neural treatment. Okay, so sometimes the peoples are means severely, they actually the young people they are severely that destroyed by the neurological pattern. So that's why they are alive, but they can speak but they cannot walk, something like that. Okay, so that is I am not much over aware over that medical science. So thing is that, but think that I have, however I have learned from some source. So these are can be their scientists are trying to that is use these radiations to improvise their neurological that is betterment. Okay, so these are the areas where you can use radiation and me, not you. Okay, radiation and you also means we. Okay, all together. So radiation and radioactive materials are safe in use properly. That is the important things. So if we take the precautions, so you'll that is it is safe for us. So many times if you have any idea, if you have gone to that medical that is for X-ray and all the things, the doctor will say that remove all the golds, that whatever the things you are wearing, you just remove that one. Okay, because that when alpha particles that will fall down on that particular material, it may give another kind of radiation. So that's why background radiation is the ionizing radiation emitted from the variety of natural and artificial radiation sources. Your exposure can never realistically be zero, because background radiation is always present. That is most important. That's why I told you those the peoples are working in case of this medical radiation, radiology, and all the segments. So they might uh, they are taking the precautions, but that might not, it is not proper that precautions for them. It is throughout the life it will be. Then background source. This is the background source. Okay. Average dose of the US of a US citizen to receive per year from background radiation is 360 millirems. See, if because it is as it is as you say that we are, I am giving you the data of USA here because we don't have data of Indian society and all the things. So see that as USA is a that is modern, so modern that country in that case. So all of things are, there is maximum radiations. You see that background radiation is that, so cosmic, terrestrial, internal, then medical. I told you the medical is 11%. Here medical that radiation is 11% is in the data. Okay, then your nuclear medicine, exactly nuclear medicine, that is what we are eating. That is so many medicines are nowadays are banned because time to time when research is going on. So nowadays also that so many countries, as we are that is cultivation country India, and so many food that is supplied to the different or export to the different countries. Now so many countries are banned this particular that is product also, because we are using so many types of medicines in that whatever things, hormones, medicines, and tranquilizer and all the things in case of that is your plantations are not actually not the organic, it's inorganic plantations are going on. That is then that's why that actually that is impact on that human body. So that's it, so many countries they are banned this product also. That is okay, no problem, that is it's going on. And consumer products also. Okay, now the things, the consumer products has the that is your radiations are there, consumer products. So consumer products means what you say that if we go to that any using of a continuously, if you are in that battery area and all the things. Okay, if you continuously you are in the battery area and all the things, you will have the so many issues. So these are the data. So which 360 millimeters of this background radiations. This dose varies depending upon where the person's lives. Just a second. Okay. So the thing is that now you'll come down to the half life. What do you mean by half life? This is the things that half life is a simple terminology which is used in case of radioactive decay. We have to understand that the fundamentals, what are the fundamentals, particles are associated with this there. So half life, so a property often used to describe or the a radioactive substance is known as the half life. I told you. So this half life is a term, is a phrase of words that is usually associated with this radioactive. Wherever you will see the half life, that means you have to understand that is there is radioactive that nature. That particular question has is from the radioactive nature of the substances. Wherever you see. Okay. So the half life is the time is taken for half of the unstable nuclei in the radioactive substances to undergo the radioactive decay. Half part any radioactive elements or any particles for the half life decay, how much energy is released, that is your half life. Because see that is full that is completely one radioactive element cannot undergoes the fully that is decay. This is not possible. It is not possible because it is inter convertible. Okay, so there is wide range of half lives of isotopes. This is the interesting one. When we usually teach the students in the regular classes of that is regarding this radioactive decay. So this is the actually the most interesting thing is that The half life of that is, you see, you have to understand that if you come down, so half life, only the half life of that decay is 30 minutes. 30 minutes. So what do you mean by 30 minutes? I'm telling you. So one particular element, if it undergoes the 30 minutes of half life, means it changes its behavior after 30 minutes. That is the thing. Means it is now it is hydrogen. After 30 minutes, it will be the helium. How could you consider? How can you find out the chemical properties of this substance? That's why that is the major things. I'm telling you, that just example I'm telling you. It's not about the hydrogen. Okay. So 30 minutes, after 30 minutes, its behavior will half life will 30 minutes. 30 minutes after 30 minutes, its chemical behavior will be changed. It is not possible to calculate the chemical properties. So that's why there is a wide range of half-lives for isotopes. Their half-life of P32 is only 14.3 days. Whereas the half-life of C14 is 5730 years. It is true. That's why C14 has no impact. Okay, that is, it is not a strong that a radioactive substance, but it is radioactive. Okay, next it will come down. Radioactive decay occurs randomly. That is, it is not known when the individual atoms will undergo the decay. However, although the decay of individual atoms is random, a radioactive substance consisting of many atoms will decay according to the known pattern. So this is the thing happening. Okay. Now see, that is if we okay, radioactive decay equation. Now this is important. So activity A, radioactivity, you can name as A, number of nuclei N that decay per unit of time. So A is equal to dN by dt is equal to, we discussed yesterday, minus lambda nt. At is equal to AE0 minus. Okay, this is the radioactive equation. We'll go through the, that is, you'll understand. I can't explain this one here in the, I'll show you in the video also. Half-life and the decay constant. This is the half-life and decay constant. This numerical part will, okay. So this is the half-life of P20, 14.3 days. Okay, that will be calculation part. Radioactive decay emission. Okay, that is, this is another important area of this radioactive nature. So radioactive decay emission, that is alpha particles, beta particles, gamma particles, or gamma rays. Yesterday I told you alpha, beta, gamma. So this is the things. Okay. Now we'll come down. Radioactive emission will the alpha particles contain two protons and two neutrons. Okay. So who will produce the alpha particles? If same number of protons and the same number of neutrons are present, if you say that in case of helium, so that is hydrogen to helium, one converted to hydrogen to helium. So two protons are present, two neutrons are present, they have an atomic number 2. So this is alpha particle emissions. Okay. Now if you come down alpha properties, heavy particles and carry charge. These are the heavy, very heavy particles and carrying the charge. They cannot travel very far due to the heavy that particles. It cannot travel very far. They typically travel up to a few centimeter in air, few centimeter, depending on their energy. So how much energy is associated on the basis of that. That's why after that it will be convertible. Not generally considered to be an external radiation hazards, as they cannot penetrate the outer protective layer of the skin. Okay, these are this if we say that helium, that radiation, that alpha particles, helium radiation of alpha particles, which two that protons and two neutrons are present, that cannot pass to the human skin. So that's why it is not hazardous for the human body. Okay, alphas can be inhaled and through further decay. Irradiate long tissue, and in case of radon and its daughters. Okay, so sometimes people that is, as it is not penetrated through that skin due to that protective layer. So it can go through the lungs also, which nasal holes, and inside the human body may cause some radiations. Okay. Then radiation active beta particles. Beta particles simply electrons. Beta radiation is a stream of electrons from the nucleus of atoms. So this is due to the electrons radiations, as I told you. So as electrons also take part in the radiation, but this is, as you know, that radiation means what is the when the something is going away from the atom, so energy level is lower down. How much energy is lower down? So that is the radiations. So this is simple radiation terminology. Beta. So as you know that electron is also passing that it is lower down its energy. So that's why in the to make the stable format, it is also radiations. Properties of a beta particles. Beta particles are either an electron, negative charge, or positron. I told you 17 charge particles are there. So positron is also one particles. Electron, neutron, proton, and this is positron. Okay, charge. Travel about 12 feet per mass electron volt in air, and that is higher energy betas should be shielded with low Z materials of such as the. Then typical beta isotopes. So these are the typical beta isotopes under that basis of radioactive emission. So this is the another thing. Emission is the most important. Where radioactive emission means there is hazardous rays. So gamma rays are high energy form of electromagnetic radiations. They are similar to the light waves but have shorter wavelengths and are more energetic. Okay, properties of a gamma ray. Gamma rays are proton that originates from the nucleus of the atom, don't carry a charge, can cause ionization when they interact, should be shielded with high Z material. Z means atomic number. Materials such as the lead if appropriate. The possible gamma emitters: nitrogen 22, carbon 36, then indium 125, 131. These are the so properties, characteristics of X-ray. Characteristics of X-ray are generated when electrons fall from higher energy to lower energy electron cell. It is higher to lower, then energy will be emitted. That is your X-ray. So properties of Bremner X-rays. Bremner X-rays are created when the electrons are slowed down in the field of the nucleus. Then penetrating power. The penetrating power of the radiation varies in part due to their masses and their charge. Protection from the radiation distance and shielding. Okay, so if you make your distance more distance, then you can protect yourself. Penetrating power. Alpha outside the body, little damage, not able to penetrate skin. Inside the body, cause much damage or to the tissue, cell, DNA, and proteins. So if you pass through the nasal holes, also it can create the damage, alpha particles. But in the skin, so it cannot be damaged much more. Beta, some harm but much less than the alpha and can go through the skin. It is less because, as you know, that it is associated with the electron. So that's why. Gamma is the most harmful, easily penetrate skins. That's why that is X-ray machines are used that gamma rays, which X-rays the internal parts. You can see that bones and all the things. It is most harmful, easily penetrate skins and damage DNA and cells as it rips through. Exposure. So elements tend to the concentrate in certain part of the thyroid skin. You see that picture where it is written there, bone and throughout. Okay. So radiation units, there are specific units for the amount of radiation you can receive in given time for the total amount of exposure for the subject. Okay. The measuring radioactive rates. This is an important area for measuring radioactive rates. This is the amount of a radioactive in a sample. The amount of radioactivity is equal to activity. A commonly used unit for the measuring of the activity is Curie, as it in that against the name of Sir Curie and Madame Curie. 1 Curie is equal to 2.2 in 10 to the 12 disintegration per minutes, DPM, disintegration per minutes. Typical activity found in the university lab are in the micro Curie and millicurie range. So measuring radioactivity rates, what is the Becquerel? Okay, Becquerel. So the amount of radioactive materials which decay at the rate of one disintegration per the seconds. This SI unit is radioactive material or activity. So CPM and DPM. CPM is the counts per minute that is detector sees. DPM are the actual disintegration release of the radioactive samples. So since detector are not 100% efficient, DPM is equal to CPM by detector efficiency. Radiation dose versus rate. So these are the things. Okay. So these are the things. It's not much more important for you. Okay. Now I'll go to that. I'll stop this one. I'll go to that video. So check it out. The video also. Just a second, please. Just a second, please.
Of radiation on human health. My presentation on this particular topic outlines the four important things. First is introduction to radioactivity, sources of radionuclides, background radiation, application of radioactivity. This is one of the important symbols which you might have come across at many places, which talks about there is radiation in hospitals, in industries. This place shows that there is a radiation at that particular point. Now, we should know what is radioactivity, how radioactivity is defined. If you see the literature, nuclear decay or radioactivity is the process by which a nucleus of an unstable atom loses energy by emitting ionizing radiation. A material that spontaneously emits this kind of radiation, which includes the emission of alpha particles, beta particles, gamma rays and conversion electron. So this tells what is radioactivity. We all know these two important laureates. First is Anthony Henry Becquerel and Marie Curie. Because of this, only there is a term radioactivity defined, and now today in the world we are using radiation for many useful purposes. The important question which comes to our mind, why are elements radioactive? Why we say this element is radioactive and this not. We all know there are unstable nucleus. Unstable nucleus means they have excess energy. And when they have an excess energy, as a law of nature, everything wants to go to the ground state. So this unstable nucleus, which is having excess energy, they would like to come to a ground state. And thus, when it comes to ground state, they emit different kind of radiations. The radiation which is being emitted while coming from unstable state to a ground state are ionizing radiations. This is very important pictorial picture or pictorial graph which tells about the radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. If you see this particular picture, we can find out the wavelength decreases from radio to gamma, and in the way the wavelength decreases, the frequency increases because wavelength and frequency is inversely proportional. It shows below that there is a building which talks about radio and there is an atomic nucleus which talks about gamma rays. This is called an electromagnetic spectrum. Now, we want to know, we should know what are the sources of radioactivity. As we understand, there are three different sources of radioactivity. First is called primordial radionuclides. That radionuclides that are present since the creation of Earth and having a half-life much longer. Talked about lead, radium, potassium. We have potassium in our body also. Now similarly, there are second kind of radioactivities are defined as cosmogenic radionuclides. That radionuclides that are produced in the upper atmosphere as a result of cosmic rays, interaction with light particles like carbon atom and oxygen, and we get different radionuclide like carbon-14, beryllium, sodium, phosphorus and sulfur. These are all radioactive material. Now comes the last in which this category is defined is called anthropogenic radionuclide. That radionuclide that are produced as a result of man-made activities such as nuclear fuel fabrication, enrichment, nuclear power generation, nuclear accidents, etc. And you know, whenever such incidents takes place, we got a radioactive material like cesium-137, cesium-134, iodine and strontium. It means we have defined radioactivity in three different forms or three different parameters: primordial, cosmogenic and anthropogenic. Now, if you see this particular picture, it talks about the sources from where it emits. It goes to the atmosphere, then comes to the man or animals, then comes to the plant, and plant it goes to soil. From soil it may again go to plants and plants to man. What does it mean? What is natural background radiation? The natural radiation energy between few kilo electron volt to mega electron volt from primordial radionuclide are called background radiations. As we defined in the previous slide, what is primordial background radiation? The radiation which is coming from in the range of kilo electron volt to mega electron volt, and these are background radiations, and they may be in a terrestrial or extraterrestrial origin. So this particular picture tells about the source. It goes to the atmosphere or it may come to the soil. When it goes to the atmosphere, it may come to the man or animal. From man and animal, it may come to the plants, and if you see the reverse cycle, from plants it may be taken up by man or animals. Similarly, when it comes to the soil, from soil it goes to the plants, or if it comes to the plant because of man and animals excreta, it goes to the soil. So these are what it is called background radiation. Now, artificial radionuclides. We all know, we have read in the literatures, in our books, there are two different kind of radionuclides. One is artificial, one is man-made. Over the last few decades, Man has artificially produced hundreds of radionuclides for various purposes in medical, for industry, for research, for agriculture, and these artificial radioisotopes to the atmosphere during the course of operation nuclear fuel cycle, nuclear test and nuclear accidents. Most of the artificial radioisotope decay having short half-lives. Therefore, only few of them are significant from the point of human exposure. What do you mean by short half-life and long half-life? That we are going to discuss in next few slides. The question comes, artificial radionuclide, when we are making it or producing it, there may be some advantages for that. First of all, when we are dealing this particular module, there are certain key definitions which we should also know. Until unless we will not be able to understand the radioactivity. Few terms which comes when we define the word radioactivity is Z. Z is nothing but atomic number. It is the number of protons in the nucleus of an atom. Nucleus, what is nucleus? It is nothing but a proton and neutrons which are located in a form in an atom is called nucleus. Now comes proton. Positively charged particle in the nucleus of atom is called protons, and mass is nothing but 1 AMU. What is neutron? Neutron are the particle which are neutrally charged. It means they don't have any charge. As we define the proton a positively charged, electron the negative charge, neutrons don't have charge, but neutron and proton both combine to make a nucleus. And comes mass number of an atom, number of protons and number of neutrons in the nucleus is called mass number. Now it means we have defined what is atomic number, what is proton mass number, and what are different type of particles like proton, neutron, electron, and proton, neutron both combine to make a nucleus. Now see this particular picture, how beautifully defined the radioactive decay whenever the decay takes place. Why the decay takes place? Because at which are unstable, they want to come to a stable state. How they can come to the stable state? We should know the neutron by proton ratio. If there is a neutron per proton ratio is not same, it is much higher, it is going to decay to become stable. This particular picture talks about alpha decay, beta decay, gamma decay and neutron. Now there are three common types of radioactive emissions. One is alpha, one is beta, one is gamma, and they are all prominent in nature. We all come across in day-to-day work three different kind of radiations emission like alpha decay, beta decay and gamma decay. What is alpha decay? How to define alpha decay? You have seen the americium-241 isotope. When it decays to neptunium-237, how when it decays, it comes out an alpha particle. What is alpha particle? That will come across the next slide. Then there is a decay called beta decay. When tritium comes to helium-3, there is a decay called beta decay. It clearly shows when the beta decay is taking place, electron is coming out. Similarly, gamma decay. Gamma decay is nothing but when an isotope comes to the other state of an isotope, there are some excess energies there in the nucleus which comes out in the form of some radiation, and they are called photons. It means we have three different kind of decay, alpha, beta and gamma, and most of the radioisotope decay by this particular mode. Since last few slides we are talking about a nuclear stability. What is nuclear stability? There is a neutron by proton ratio. What is neutron by proton? It means the nucleus, there are neutrons, there are protons. If neutron by proton ratio is 1, it means the isotope is stable. But when there is a change in the neutron by proton ratio, then it means the nucleus is unstable. And so what happens? Either neutron convert to proton a proton converts to neutron, so their kind of reaction, and unstable nucleus comes to a stable. This is a belt, a graph we all see whenever we talk about radioactivity in books. Is a nucleus stability belt. Now, in the few slides back, we were talked about the kinds of radioactivity. Summary of radioactive decay, if we talk about alpha, beta, gamma. But apart from that, there are two different kinds of emissions called positron emissions and electron capture. When we talk about alpha particle, as I was discussing, there is a decay. Particle emitted is helium nuclei. What happens when a helium nuclei comes about? What happens to the mass number? The mass number decreases by 4 and atomic number by 2. When beta decay takes place, what happens? When a beta particle emits, there is no change in the mass number, but atomic number increases by 1. When gamma emission takes place, again, no change in the mass number, no change in the number of the atomic number, but there is emission of energy, and that energy is called photons, and which is called gamma emission. We come across positron emission and electron capture. There are two different kinds of emissions. In case of positron emission, particle emitted are positron. What happens to the mass number? No change. What happens to the atomic number? Decreases by 1. When we talk about electron capture whenever takes place, it means there is a vacancy in the orbits. When electron capture takes place from K shell by nucleus or from L shell to K shell, then what happens? There is a change in the energy. The vacancy is created, and because of the vacancy, the photon is coming out, energy is coming out. If it is coming out from K shell, it is called K, otherwise it is called X-ray photons, and there is no change in the mass number or atomic number. Yes, atomic number again decreases by 1. It means when a positron emission takes place or electron capture takes place, both have same kind of effect, that atomic number changes by 1. Now, there are 3 different isotopes. What is isotopes? They are the atom of same element that a different number of neutrons. If the neutron changes, it means electron and proton, like we talk about 3 different isotopes of hydrogen. One is protium, second is deuterium, and third is tritium. It means 1 proton. In case of deuterium there is 1 proton and 1 neutron, and we talk about tritium, there is 1 proton and 2 neutrons. So there are 3 different isotopes or radioisotopes of hydrogen, because there is change in the proton in all the 3. Protons are same, but neutron there is a change. Now we have dealt in the previous slides about different kind of radiation, but we should know now what are the unit of radioactivity. Becquerel is the unit of radioactivity and is defined as disintegration per second. What is Curie? 1 Curie is nothing but 37 or 10 to 9 becquerels. So 1 millicurie is nothing but 37 megabecquerel. It means 37 into 10 to 6 becquerel. When we talk about 1 microcurie, it is nothing but 37 kilobecquerel. The second important unit is RAM, Röntgen equivalent man. RAM is usually a term used to describe the equivalent or effective radiation dose. In the internal system of unit like SI units, sieverts is the unit of dose, which is nothing but describes an equivalent effective radiation dose, and usually defined at 1 sievert is nothing but 100 rams, or 1 grays 100 rads. Now comes to the important term radioactive half-life. What is radioactive half-life? Usually all radioactive elements, they decay, as we are discussing in the previous slides, and when they decay, they comes to the second state or ground state or other isotope form. The half-life of an element is the time that it takes for half of the material you started with to decay. It means We started with x. After some time, when it becomes x by 2, it means the half-life is, it defines the half-life. It does not matter how much you start with. After one half-life, half of it will have decayed, half of its original quantity. Each element decays into a new element. Like carbon 14 decays into nitrogen 14, while uranium 238 radioacid decays into lead 206. Half-life of each element is constant. It is like a clock keeping perfect time. Whatever in the physical or chemical form the radioisotope is there, half-life never changes. Half-life is always the life in which half the radionuclide decays from its original value, and that remains constant. This particular picture, if you see, radioactive half-life. Half-life starts from uranium-238 and how it is coming to lead-206. Various decays are taking place from alpha, beta, then there is certain change of energies, and now the way it comes from how many years, 10⁵ years to 10⁻, and finally it comes to lead-206. This is how typically we define the radioactive half-life. Now, when we see this particular picture, how much of this element remains after 4 half-lives? As we define, 1 half-life means half of its element is remaining. Now, one more half-life goes, 2 half-life means again half. The third, again half. It means when we started with 100%, the first half-life it goes 50%, second half 25%, third life 12.5, and similarly it goes 6.25%. In this way, the half-life is defined. Half-life may be in years, maybe in days, maybe in seconds, maybe in minutes. Now there are different types as we talk about alpha, beta particle and gamma. This particular picture, if you see, it clearly shows about whenever alpha particle comes out, the 2 neutron and 2 proton comes. Beta particle, either electron or a positron. And gamma is nothing but photons. It is always called X-rays, gamma rays. This particular picture clearly tells about what are the different kind of materials are required to shield this particular radiation. Like alpha, a paper is good enough. For beta, even hands or skin can good enough. But for gamma and X-rays, we require a concrete. It's a beautiful picture about radiation penetrating power. The race starts between alpha, beta, gamma. Alpha, paper can be stopped. Beta can be stopped by glass. Finally, who is winning the race is nothing but gamma, who has crossed paper, able to cross glass, and finally lead. If the lead is not equivalent thickness, the thickness of lead is not proper, the gamma comes out, and see, it talks about I win the race. Again, similarly, we have again defined the pictorial graph of alpha, beta, gamma. Alpha particles may be completely stopped by sheet of paper, beta particle by aluminum shielding, and gamma rays, however, can only be reduced by much more substantial objects such as a very thick piece of lead or concrete. Is radioactivity gives health problem? We talked about alpha, beta, gamma. They are all ionizing radiation. What do you mean by ionizing radiation? It is going to do the ionizing of the matter. It means when it comes and interacts with the body, definitely some reaction takes place, some effects takes place. And alpha, beta and gamma particle all add energy to the body tissues. The effect is called ionizing energy. It can alter DNA. Even though alpha particle is not very penetrative, if the decaying atom is already in the body, like inhalation, but they can cause trouble. It means when the radioactive material is outside the body, you are going to give an hazard. But when it goes inside the body, because of inhalation and ingestion, it is going to decay and it is going to harm. Alpha, beta is going to harm, but gamma may come out. The important 3 principles, which are called cardinal principle, by which we can able to shield the material or shield this particular radiation is by time, distance and shielding. These are three principles which talks about that you can able to protect yourself. If at all you are going to be with minimal time with the radioactive material, then you are going to be less exposed. If you are going to handle radioactive material large distance, then again exposure is less. And if you use some kind of shielding material, as we discussed about paper, aluminum, glass for beta particle like or concrete or lead, you can able to protect yourself. Now this particular slide, if you see, there is an X-ray machine. What is happening? It is giving some kind of radiation. You are able to get the picture of the chest X-rays, a film, and finally you come out. The person who is coming out is not a radioactive person. He doesn't have any radiation, but he has been exposed and got the film. Dose or radiation dose is a generic term for measure radiation exposure. In radiation protection, dose is expressed in milliramps. We talked about the quantity RAM. Now, when we are using a solid material, solid radioactive material, or a radiation generating equipment like X-rays and all, we are going to get exposed. But the situation changes when the material is in the form of liquid, because while handling liquid radioactive material, there is chances of contamination. But contamination is what? It is the presence of radioactive matter in any place where it is not desired, and especially in any place where its presence could be harmful. So if there is a spillage and which can lead to some kind of harm, it is called contamination. Now this particular slide talks about the medical application. As we told, when we talk about radiation or radioactive material, it is having certain parameters or certain applications. Radioisotopes with short half-lives are used in nuclear medicine because they have the same chemistry in the body as a non-radioactive atom. In the organs of body, they give off radiation that exposes a scan giving an image of an organ. It means suppose you would like to take a thyroid scan, would like to know how the thyroid is functioning. You give a radioactive material, it starts emitting some kind of radiation, it is to be detected with a detector, and a scan is produced. It is nothing but a thyroid scan, which tells your doctor whether your thyroid is functioning normal or abnormal. Now comes to the application of radiation in industry, leak detection. This use of radionuclide tracer to find the leaks of flow path has wide application. Industry. Finding the location of leaks in oil well castings, determining the tightness of abundant slate coils for the temporary storage of oil, looking the position of leaks in refrigeration coils, finding leaks in heat exchanger piping, locating leaks in engine seals. It means the places with the flow of liquid. If you want to know any leakage has taken place, radioactive material plays a very important role. This slide text talks about when there is a flow of liquid and we would like to know how much, at which particular point there is a leakage. Then what happens? You just, with the liquid, you give some kind of radioactive material as a tracer. When the tracer flows, some radiation is being emitted, and the place where you find that the holes are there or some leaks have taken place because of the joints crack and all, you find the counts change, there is a change in the count. So this is the way to find any leakage in case of lines where the liquid have been flowed, where you cannot able to open and find out. If you want to control the thickness, we all know papers have been produced. The manufacture of aluminum foil, if you want to see it, the aluminum foil manufacturing is going on, but we have to maintain the thickness of this particular foil which is being produced. How it can be done? Beta emitter is placed, beta is emitting, radiation is coming out, detector is there, and finally we have a computer. This computer tells about by a system if there is any change in the thickness, and finally it feeds to the roller, and roller then maintains the thickness. Now this is very important thing. We always know carbon dating. When a living tissue is there is a carbon 14 by carbon 12, there is a ratio. which is same as atmospheric ratio. If the change is taken place, you can able to find out, yeah, change has taken place, and with that possible dead tissues. Now this mummy you can find out, which is frozen in the Italian Alps. Now if I would like to know okay, how old it is, by using carbon dating, we can able to find out. And this particular mummy is 1991, it was found out, and we can able to find how old it is, at least 5,000 years old. The importance of radionuclides, as we have seen in case of agriculture, we can able to do the improvement of the crops by mutation techniques. The crops which gets, we can say, which the life of the crop, you can increase the life of the crop by using this particular radiation. As you can able to see that when the radiation comes on the seeds, then the mutant cultivars and how it takes place, and when there are no negative mutations and when there is no mutation, how it changes. Insect pest control. You can see this radiation which is very very useful in case of agriculture where the insects are there. How to really control this particular insects. It can be used as a pest control, and you full particular type of this you can able to control this particular insect which is going to create a problem for our crops. Preservation of food and agriculture product by radiations. You might have come across different kind of potatoes, onions and different type of spices where we increase the shelf life by using radiation. This is one of the alternate method of food preservation by irradiation of X-rays and gamma rays. It is used to prolong the shelf half-life of many food and agriculture products. It destroys bacteria and microorganisms in food, pre-packed or bulk and grains. The food exposed to controlled amount of ionizing radiation in shielded area for specific time to achieve desirable objectives. So what does it mean? It means we are trying to increase the shelf half-life of the food by exposing different kind of radiations. The sources are gamma rays from cobalt-60 or cesium-137, X-rays up to 5 electron volt, electron accelerators also being used up to 10 mega electron volt to preserve the food and agriculture product. See how the food has been preserved by giving the dose from 0.05 kilogray to 0.15 kilogray. It means the onion and potatoes we can preserve by using different kind of radiations. Now see radioactive consumer products. We all know smoke detectors, their watches were there. What happens? They have radioactivity and it shines. Very small amount of radioactive materials are being used in these products which are called consumer products, which doesn't have any kind of harms, but it is very very useful for our day-to-day work. Dentures, initially in dentures also it has been used. This particular thing is very well given in the literatures that very small amount, less amount of concentration of quite low, it has been used, but now we have stopped because of the harmful effects. It means to say that there are the uses in every application. Radiations are there many places, but some of the places we have to stop, like dial painting, in dentures, etc. Now this particular slide tells about the sources of background radiation as of now. Radon, if you see the cosmic rays, it gives 8%. Terrestrial rays gives 8%. Way it should not give any kind of harms, like while electron carries a negative electrical charge. These forces within the atom work towards a strong, stable balance by getting rid of excess atomic.
Okay, these are the things what I told you. On the basis of that, I showed you video you just for the better understanding of all these things. Let's understand the half life of that one. So I'm sharing another video also. Let's understand radioactive decay law. Let's understand radioactive decay law by observing this video.
Law, radioactive decay. Before you do that, please don't forget in the bottom right hand corner, click on that red button, subscribe to my channel, get all my excellent physics, radioactive decay law. And of course, really in physics, the laws are kind of best explained by the equation, and this is the equation which we'll talk about in just a moment. But really, what radioactive decay law says, or what really radioactive decay is that the number of parent nuclei in a radioactive sample decreases exponentially over time, and that's due to the half-life. So if you have some amount of sample, after one half-life, you'll have half the number of radioactive nuclei. Another half-life, you'll have another half, so it goes down by half again. So you start off with a whole, then you go to a half, and then you go to a quarter, and then you go to an eighth and 16th, and that's exponential decay, and that is radioactive decay law. This is the equation, one of the equations we use to calculate different things for radioactive decay law. Let's just start with all of these things. Let's just start with this one right here in the middle. That's a good place to start since that's N0, and N stands for the number, and N0 is the number of radioactive nuclei at time t equals 0. So sometimes we say we have a certain number at this point and how many we have later. Okay, then we can figure that out. But N0 is the number that we have at time equals 0. NT is the number of radioactive nuclei that remain after some time t. So it could be after 100,000 years, after 20 seconds, after 1,000,000 years. How many radioactive nuclei do we have left if we started with this number? Okay, so that's N0 and NT, and it's just for the number of things, in this case radioactive nuclei. E is Euler's number, which you should have a button for that on your calculator. If you don't, you can just approximate it as 2.718. All right, and then E is raised to the power. So this is raised to the power of minus negative. This is lambda. And in this case, for lambda is the decay constant. We'll talk about what the decay constant is in just a moment. And then T is the time that occurs. And really what it is the time that occurs between these two number of radioactive nuclei. How many you had at the beginning and how many you had at some time T later. And we can use this equation to calculate for all of these things, including half-life, number at the beginning, number at the end, the time that occurs. Okay, so we can we're going to do a quick example at the end for one of those, and then I'll make some additional videos showing how we can use that to calculate some other things. So I wanted to point out that we have this equation, which is we often refer to as the radioactive decay law, but we have two other equations which are basically, you might say the same or very similar, and that is because this equation we use for when we're talking about the number of nuclei. So if you have a problem and it talks about the number of nuclei, then you use this equation. But we can also do the same thing with the activity, because the activity is directly related to the number. Okay, activity is defined as the number of radioactive decays per second. Well, if you have less radioactive nuclei, then you're going to have less decay. So we can use the same equation that we have for activity. And of course, the number of nuclei, or the number of atoms, is directly related to the mass. So you can also use this equation for the mass. You'll notice all of these equations, all three of these equations, are essentially the same. In one case, we use the number of radioactive nuclei. In this case, we use the activity. And in this case, we use the mass. But they're all the same, exponential decay. And you can see that if you look at the graph of each one. Okay, so here I just made a graph showing what a typical decay curve would look like for the number. This is for the activity, and this is for the mass. And the graphs look exactly the same. They have the same shape. It's just you're using a different counting system. In this case, once again, it's the number. In this case, it's the activity. And in this case, it's the mass. Okay, so this is expressed as a percentage. Start out with 100%, one half-life, you have 50. Another half-life, you have 25, and then you have 12.5, and then 6.25, and so on. And the activity is the same. You have half, then you have a quarter, and then you have an eighth, and the 16th. The mass, you have half as much mass, and then second half-life, you have a quarter of the mass. So those three guys, it's kind of important to understand that those three graphs look exactly the same. Okay, now I think we're going to try a problem out here. Okay, let's say we have this problem and we have a sample of material that contains 1 milligram of iodine 131. And this is a little background information. It's kind of interesting. This is an isotope that's used in very small doses, less than 1 milligram, for thyroid cancer therapy. It's also a byproduct of nuclear fission, and it has a relatively high decay rate. It's considered to be, highly active because it has a high decay rate because it has a low, short half-life. The half-life is only 8.02 days. And we want to know if we have 1 milligram of iodine 131, we want to know the number of atoms of iodine 131 that were initially present, and we need to know that so that we can calculate the number of iodine 131 atoms that are present after 50 days. Okay, we know the half-life, we know the initial mass. We're going to take that mass, okay, and we're going to convert it into the number of radioactive nuclei, and we can do that using a little bit of, you might think of chemistry or stoichiometry. We have 1 milligram, which is 1 times 10 to the minus third grams of iodine. We know that you can look up online and look up in a book and in the appendix somewhere that the molar mass of iodine 131 is 130.91 grams. So we're going to convert from grams to moles, and that tells us that we have 7.64 times 10 to the minus 3 moles. We want to know how many atoms we have. So we know that 1 mole is 6.02 times 10 to the 23rd atoms. And we come out with 4.60 times 10 to the 21 atoms. That's what is present in 1 milligram of iodine 131. All I did was take this number, divide by this number, then I take the result and I multiply it by 6.02. And I get 4.6 times 10 to the 21 atoms. Now, we are going to use this equation. This is a common kind of problem. We want to know how many we have left. Right? That's this. This is the initial number, 4.6, and we want to know how we're going to have after 50 days. So we're going to solve for NT. Of course, this equation is already solved for NT. And we know N0, which we calculated in the previous slide. We know E is a constant, so to speak. We have to figure out first what the decay value is here, and then the decay constant, and then we know the time is 50. So we have to figure out this value first, and that is simply calculated as the natural log of 2. It's always the natural log of 2 divided by the half-life. Now the half-life was given to us as 8.02 days. So we're just going to take the natural log of 2, which I believe is 0.693, divide that by 802, and we get that the decay constant for iodine 131 is 8.64 times 10 to the minus 2. Now, sometimes you'll see people convert this into becquerel or into seconds. They could convert this into seconds first because they want to know the activity, because activity is expressed in decays per second. But we're going to leave this as days because our time up here is days, and you see that when we plug that into that equation, this equation right here, that the days are going to cancel and we'll be left with a number, okay? So all I did was I wrote the equation down up here. All I did was plug E, I usually leave it as E. You could write down 0.693, and it's raised to the power of minus, don't forget the minus, 8.64 times 10 to the minus 2 days. Now this is days to the minus 1. We were dividing by days in the previous slide. So this is 1 over days, and this is times 50 days, and then this day and this day will cancel, and we won't have any units except this has the units of number of nuclei. Okay, but the days will cancel. So that's why we left that as days. You can't convert that. You can't have this be seconds and this be days, or this be days and this be years. It has to be the same unit, whatever unit you want to use. And then we just do that. I just showed you one step here. I took this value raised to this power, and that's 1.33 times 10 to the minus 2, and you multiply those two together, and you get that the number of radioactive nuclei, or the number of atoms of iodine 131, which has a half-life of 8.02 days. If you start off with 1 milligram, after 50 days, you'll have 6.12 times 10 to the minus 19 atoms of iodine 131. So there you go. Thank you very much for watching. Hope you found that video helpful. If you did, please do all the following 4 things. Please subscribe.
Okay, that is all about the radioactive decay law. So it is important for your syllabus and all the things. Let's see another thing also. Just a second. Let's make it clear one more thing is alpha, beta, gamma radiations by looking this video.
Firstly, let me teach you that what are radioactive elements and radioactive decay. Well, consider big atoms like uranium. The nucleus of uranium has excess energy, due to which uranium is unstable. Now it will release this energy in the form of radiations. When uranium releases this extra energy, it will get stability. So uranium is a radioactive element because it is unstable due to extra nuclear energy. Therefore, we define radioactive elements as the unstable elements having excess nuclear energy to produce radiations and get stability are called radioactive elements. Let me repeat it. The unstable elements having excess nuclear energy to produce radiations and get stability are called radioactive elements. Some other common radioactive elements are polonium, radium, and thorium. While radioactive decay is defined as the process by which an unstable atom loses energy in the form of radiations is called radioactive decay. Consider this radioactive element. We know that it is unstable and its nucleus has extra or excess energy. This radioactive element will release excess energy in the form of radiations and it will convert to daughter isotope. This whole process is known as radioactive decay or nuclear decay, or we just call it radioactivity. Hence remember that radioactive elements undergo radioactive decay or nuclear decay. Now let me teach you that what is radiation? Well, it is energy that comes from a source and travels through space at the speed of light. For example, the sunlight or visible light is a form of radiation and its source is the sun. We call it solar radiation. So remember that radiation is a form of energy. Now there are 2 types of radiations, non-ionizing radiation and ionizing radiation. Non-ionizing radiation has enough energy to vibrate atoms in a molecule. For example, radio waves and microwaves are the non-ionizing radiations. They have the ability to vibrate or high energy to knock electrons out of atoms. For example, alpha radiation, beta radiation, and gamma radiation are the ionizing radiations. When gamma radiations fall on an atom, they can remove an electron out of atom. We know that when we remove an electron from an atom, this process is called as ionization. So we call gamma radiation as ionizing radiation because they ionize atoms or they have the ability to remove an electron from the atoms. Thus note down all these important points. Now let me teach you the type of ionizing radiations. The first type of ionizing radiation is alpha radiation or alpha particles. We already know that in radioactive decay, alpha particles are produced. Alpha particles are double positively charged. They are made up of 2 protons and 2 neutrons. They have no electron. It is exactly the same like a nucleus of helium atom. We represent alpha particles by helium nucleus He. Remember that alpha particles are relatively large, that's why they can easily be stopped by a paper. So we say that they have less penetration ability and can travel a few centimeters in the air. On the other hand, due to large size and large charge, they have strong ionizing power. That's why they can easily knock electron out of atom after collision. Hence noted down these important points. The second type of ionizing radiation is beta particles or beta radiations. In nature, beta particles are just like electron, and we know that the charge on electron is -1. Secondly, its mass is negligible. Relatively, beta particles are very tiny. They can easily penetrate through a paper, but they are blocked by a word. For example, they can travel several meters in the air. Thirdly, due to tiny size, they have moderately ionizing power. Hence noted down all these important points. The third type of ionizing radiation is gamma radiations. They are waves of electromagnetic radiations. They are emitted only or after the emission of alpha and beta particles. We know that electromagnetic waves have no mass and charge, so they can easily pass through different materials. That's why they have strong penetrating power. They can travel far in the air. We need thick sheet of lead in order to stop them. Remember that they have weak ionizing power. One last part of ionizing radiation is neutron. Remember that if an atom has too many neutrons, there is possibility that it will remove or given off this neutron in order to get stability. Hence noted down all these important points.
Okay. So this is that all about the things. But tomorrow is the last class of this your MCH-4. So just a second, please. Okay. In this case, we have to understand the radio analytical methods and all the things. Okay, that is what are the methods, are direct method, indirect method, and all the things, techniques, and all the things we have to understand. So tomorrow that is with the MCH-4 last class. Perhaps your that anyone is there in line.
Yes, sir.
Yes, sir. Yes, sir.
Okay. So that is that your past semester syllabus has completed, perhaps MCH 1, 2, 3, 4.
Right, sir.
Okay. So wish you all the best. Tomorrow is the last class, and if anyone has any doubt, you just log in me in that WhatsApp group. You can ask anything else. Some students have some issues, so I can sort it out. Hope that you have done all the assignments and all at right time. You have to submit that one. Okay. So thank you very much for your time.
Okay, sir. Thank you, sir.